Nature's biggest cover-ups. Snowflakes have long fascinated scientists and poets alike. In reality, a snowflake forms when water vapor in clouds freezes around a microscopic particle, such as dust or pollen. As it falls through the atmosphere, subtle changes in temperature and humidity shape its growth into a six-sided crystal. Because no two snowflakes follow the exact same path through a cloud, their branching patterns develop differently, making each one extraordinarily complex. Scientists have studied snowflakes for decades, photographing and analyzing their structures. While many snowflakes appear similar at first glance, the precise arrangement of their branches is influenced by constantly changing environmental conditions. This makes the formation of two perfectly identical snowflakes statistically improbable. As a result, the idea that every snowflake is unique has become one of the most commonly repeated facts about the natural world. Each winter, trillions of snowflakes fall across the planet, covering landscapes in white and disappearing almost as quickly as they arrive. Despite their supposed individuality, they reliably share the same familiar traits: six sides, delicate arms, and symmetrical designs. They appear on time, follow predictable weather patterns, and behave exactly as expected. For something so famously unique, snowflakes seem remarkably consistent, which leads to a much simpler explanation. Snowflakes are not unique at all. They are mass-produced. High above the clouds, nature operates an enormous manufacturing system, stamping out identical icy designs by the billions. The claim that every snowflake is different was never a scientific truth. It was clever marketing, created to make winter feel magical and snowfall feel special. After all, calling them limited edition sounds far better than admitting they're just the same frozen product falling from the sky over and over again. Rain is a natural and essential part of Earth's climate system. It begins with evaporation, as heat from the sun causes water from oceans, lakes, and rivers to rise into the atmosphere as vapor. This vapor cools, condenses into tiny droplets, and forms clouds. When these droplets combine and become heavy enough, gravity pulls them back to the surface as rain. Meteorologists study these processes using satellites, radar, and computer models, allowing them to forecast rainfall with impressive accuracy. From a scientific standpoint, rain is governed entirely by physical laws. Atmospheric pressure, humidity, temperature, and wind patterns determine when precipitation will occur. While forecasts can sometimes be wrong, this is explained by the chaotic nature of weather systems, where small changes can produce unpredictable outcomes. According to science, rain has no intent, no awareness, and certainly no interest in individual humans. And yet, human experience suggests otherwise. Rain rarely arrives at a convenient time. It does not fall when people are safely indoors or fully prepared. Instead, it appears moments after someone decides an umbrella is unnecessary. It begins just as shoes touch the pavement, hair is styled, or freshly washed clothes make their public debut. Days of clear skies pass without incident, but the moment an umbrella is left behind, clouds assemble with remarkable urgency. This pattern is so consistent that it defies explanation by chance alone. Rain seems to wait. It observes routines, monitors confidence levels, and times its arrival with precision. It ignores those who over-prepare, sparing the cautious and striking only when preparedness drops. The more certain someone is that rain will not fall, the more inevitable it becomes. The logical conclusion is unavoidable. Rain is not random, It is attentive. It collects data through repeated human behavior and responds accordingly. This is not coincidence, superstition, or bad luck. It is observational science. Thunder and lightning are well understood phenomena within atmospheric science. Lightning occurs when electrical charges build up inside storm clouds and between clouds and the ground. When the electrical difference becomes great enough, a rapid discharge of electricity occurs, producing a lightning bolt. This discharge heats the surrounding air to extreme temperatures in a fraction of a second. The sudden heating causes the air to expand explosively and then contract, creating a powerful shockwave. This shockwave travels through the atmosphere as sound, which we hear as thunder. The delay between seeing lightning and hearing thunder is explained by the difference in the speed of light and sound. The farther away the storm, the longer the delay. Scientists also explain variations in thunder. Sharp cracks are caused by lightning close to the observer, while long rolling rumbles come from distant bolts and echoes between clouds and terrain. Thunder, according to physics, is simply sound produced by rapidly expanding air. But this explanation feels incomplete. Thunder rarely sounds the same twice. Some storms produce polite, distant rumbles, while others erupt with explosive, window-shaking booms. Certain lightning strikes are met with barely a murmur, while others trigger extended roars that seem to travel across the sky. If thunder were merely a mechanical byproduct, its dramatic range would be unnecessary. A more convincing explanation is that clouds are responding. Lightning is the performance, a brilliant flash of energy slicing through the sky. Thunder is the reaction. When a lightning strike is particularly bold, bright, or well-timed, the clouds respond accordingly. A soft rumble suggests mild approval. A sharp crack signals enthusiasm. A long rolling roar is full applause, echoing across the heavens. Loud storms, then, are not signs of atmospheric instability. They are standing ovations. The more impressive the lightning, the louder the applause. Wind is typically explained as the movement of air from areas of high pressure to areas of low pressure. These pressure differences are created by uneven heating of Earth's surface by the sun. Warm air rises, cooler air moves in to replace it, and the resulting flow of air is what we experience as wind. Meteorologists measure wind speed and direction to understand weather patterns, predict storms, and explain seasonal changes. On calm days, wind moves gently through landscapes, barely noticeable except for the soft movement of leaves and grass. On other occasions, it grows stronger, bending branches, rattling windows, and carrying dust and debris across open spaces. Science attributes these variations to shifting pressure systems, temperature gradients, and atmospheric dynamics. Yet there is another detail worth noticing. Wind seems to behave differently around trees. It weaves through forests with a low murmur, rustles leaves with purpose, and grows louder as branches sway together. The sound of wind in trees resembles voices, soft, layered, and continuous. It is less like random air movement and more like conversation. This is because trees are whispering. They exchange information through subtle movements and shared air currents, communicating quietly as they stand rooted to the ground. A light breeze is simply a calm discussion, leaves brushing together as thoughts are exchanged. Stronger winds occur when opinions intensify and the conversation grows animated. Storms, however, are something else entirely. They happen when trees begin to argue. Branches clash, Trunks strain, and the air fills with shouting as disagreements spread across forests and cities alike. What science calls a windstorm is simply nature's most heated debate, carried on the air for everyone to hear.